Now we'll hear from.
I don't know if it's on.
Maybe I could just project. Hello, hello, hello. Yeah, okay. I'm just all right. Welcome back. Next, we're going to hear from Nisheeth Vishnoi at Yale, who's going to tell us about Hamiltonian Monte Carlo.
Hi, everyone. Can you hear me?
Yes.
Okay, great. So thank you for organizing this online. So this talk is going to be on Hamiltonian Monte Carlo, which is an algorithm for sampling from continuous distributions. There is an accompanying set of notes that I made available on the archive, whose link is here. So my plan for this talk is to give a very gentle introduction to a certain idealized Hamiltonian Monte Carlo. I presume that some of you here might not have seen this before, and explain it from the point of view of how it might have been arrived at, give intuition and even sketches of proofs of correctness and convergence for this method. So let's start with the problem. So we are given a function f, which takes an input from some d-dimensional Euclidean space. And our goal is to sample an input x from this Gibbs density, which is proportional to e to the minus f of x. I guess this audience doesn't need any motivation to study this problem. It arises in many, many different disciplines. And many of the methods that have been discussed earlier today, for instance, by Andreas and by Maxim, are iterative methods. And the traditional methods for sampling from such densities is to use some kind of a Markov chain Monte Carlo approach along with the metropolis filter. And at a very high level, these algorithms look like the following. So suppose you are at a position xi, at a point xi in space, and you want to figure out where to go next. So perhaps you take some information from the function. It could be the gradient, it could be the Hessian, or the value of the function on your current point. Maybe you add some noise and you come to a new point. This point is proposed as a possible point where you would like to jump to, but the metropolis filter applies some kind of an accept-reject criteria, whether you're allowed to jump or not. And that's how these methods work. Now, metropolis filter comes in because the goal of the stochastic process is to have a target. I mean, the stationary distribution should be this density function from which we are trying to sample. So if you just focus on the case of smooth and strongly locked concave pi, which essentially amounts to the function f being smooth and strongly convex, and focus on the number of evaluations to this function or its gradient as a function of the dimension, then most of these methods have a dependence, which is like d squared d or root d or something like that. I guess unlike optimization problems where we know that you can design optimization methods for functions, convex functions, strongly convex functions in bounds which are independent of d, we don't know how to do this for sampling. And that's really the goal, or the general goal of this area. I guess it's not possible in full generality, but trying to understand interesting conditions where we can go beyond at least this root d and perhaps all the way to polylogarithmic d would be one of the central goals of algorithms for sampling from such distributions. So what is Hamiltonian Monte Carlo? So this is an algorithm which is proposed by physicists, I believe. It somehow magically completely gets rid of this accept reject step. The problem with the accept reject step is that it slows down your chain. Depending upon how smooth the function is or how regular the function is, you might end up rejecting significantly. And especially as the dimension grows, the rejections might grow, and so it slows you down. So I guess an algorithm which does not require any accept reject step should be surprising to people who work in this area and have not seen this before, and that's what I'm going to tell you about. So let's start by some of the very basics. And we'll come to Hamiltonian dynamics in a little bit. So this person who appeared on the first slide is not me, it's not my grandfather, it's Hamilton. It's a person who lived in, I think the 19th century. So honoring him, the Hamiltonian is a function where there are two sets of variables now. So we introduce a new set of variables corresponding to the velocity or the momentum. So physicists like to think of it as momentum because there is mass. However, we will not distinguish velocity and momentum because in our case, there is no particle. And even if there is one, we just think of it as mass one. So with that said, the Hamiltonian you can view as we can define first as the function f of x, which is the given function, plus some not so strange looking term, half norm v square, where the norm is a Euclidean norm, L2 norm. You can think of this as the f term being the potential energy corresponding to the position variables x, and half v squared term being the kinetic energy corresponding to the velocity vector v of the particle. And this particle has, so once you define a Hamiltonian function h as a function of both the position and the velocity, Hamilton's contribution was to write down certain differential equations which predict how this particle would evolve were it moving in this potential well governed by this function f. And these differential equations, which I will explain a little bit more, are something like this. They describe how the position changes over time and how the velocity changes over the time. So the velocity change is the acceleration, and that's negative of the gradient of the potential. And the rate of change of position is the velocity. So this is not something very deep. However, I think it's still useful to think of it in this way because it allows us to generalize the viewpoint and go beyond this Euclidean or even the simple kinetic energy that we're talking about here. So given this, the Hamiltonian Monte Carlo algorithm in what is called its idealized form is actually the following. So it has steps. Steps are indexed by I. In each step, let's say the ith step, it samples a random Gaussian vector in d dimensions, this thing here, z, and it simulates a deterministic Hamiltonian dynamics, starting at this position xi with a random velocity c for some time t, which is a parameter of this algorithm. And here you can see a little GIF if it's clear. If it's not, that's okay. So from time to time, the particle is stopped and its velocity is refreshed. So it's really as simple as that. So the only thing that we have to figure out is what time t shall we pick. And that's really what we are going to focus most of our time in this talk. But even before that, a very basic and interesting fact, which uses all the properties of Hamiltonian dynamics, is the fact that this stochastic process preserves this density, which is e to the minus f of x minus half v squared, which is nothing but e to the minus the Hamiltonian in the position and velocity space. So the position is a d-dimensional vector. The velocity is also a d-dimensional vector. Together, sometimes they're referred to as the phase space. So the Hamiltonian is a function of the phase space of the particle. So what we'll show is that this fact is true, which is quite interesting. And this is the reason why people thought that it might be a good idea to try to run this algorithm. Of course, the obvious problem is how to simulate this Hamiltonian dynamics. These are continuous differential equations or a continuous time dynamical system. We can't really do this in a computer. So we will need to discretize these trajectories using some kind of approximations, numerical approximations, and that so once you do that, I mean that's another whole thing which I'm going to just kind of briefly mention at the end of the talk. And with these discretizations, people use this algorithm quite widely.
Nisheeth, can you clarify when you say HMC preserves density, you mean that it moves along the level sets of this density, right? Not that it's invariant, that this density is invariant.
So what I mean by this is the following, that if you, let's say, pick a point x comma v from this density in the phase space, and you take one step of the Hamiltonian Monte Carlo, which is in the first sub-step, you refresh the velocity. And in the second sub-step, you do Hamiltonian dynamics for any time t actually. Then, and when you look at the new x tilde and v tilde that you are at, the density of that point is the same as the starting density. That's what I mean. And I will make this clear, and I'll also give a proof of this. Does that answer your question?
Yes.
Okay. So yeah, I guess we're not going to go too much into discretization. We are going to look at the elegant mathematics and physics that underlie this algorithm. And my hope is to communicate that to you, and hopefully you will study this more in this semester and find connections with other topics that are being discussed. So here is a picture just to kind of give you a visual sense. You already saw a GIF, but if the GIF was not visible, then this is really what is happening. So x1 is the position, z1 is the velocity that you kick it with. It moves for some time. I mean, there's no other, there's nothing else. So it keeps moving based on the potential well. At some point after time capital T, you stop this particle and you kick it again not in the direction where it was going. This is the direction it was going, but you just give it a random turn again and you keep repeating that. So that's what is happening. And at this point, you should ask, why are we stopping this particle? How frequently should we stop it? How long do we let it go? And so on. I mean, these are the kind of questions we will try to but I mean, okay, so I saw this algorithm a few years ago and I was truly mesmerized, I should tell you. Having worked in this area, I mean, this seemed completely bizarre to me why something like this should work and why is this a good idea. So hopefully I'll give you some intuition about that.
What time?
Hello? Is there a question?
No.
Okay. So let's review Hamiltonian dynamics. And yeah, just feel free to interrupt me if you have any questions. I mean, this slide will be a one-slide crash course of Hamiltonian dynamics. I can spend time to explain if something is not clear. So we view a particle which is moving in RD, and we use xt to denote its position. But really, the particle also has some velocity, which is again a vector in RD. So you should really think of the point as moving in a 2D dimensional space or the 2D dimensional phase space. So we're going to see once we define a function h in this phase space, which outputs a real number given a vector in 2 dimensions. Hamilton wrote down these equations, which are very generic. So I just write it down here for this particular Hamiltonian. You can think of very complicated Hamiltonian in particular if you start allowing this norm by which you're measuring the length of V to depend on the position X, okay? Then you start getting what is called the Riemannian Hamiltonian Monte Carlo, which I'm not going to talk about, but for people who would know, I think this question kind of came up in Andreas's talk, so I just wanted to make a slight remark here. that you can consider very general functions, you can consider non-separable things and so on. And you'll see the limitations computationally once you think more about it. But once you have an Hamiltonian, Hamilton's equations were the following, that the rate of change of the position, so at, this is how the particle will evolve now in the phase space. dx by dt is the partial derivative of h with respect to the the velocity vectors, which in this simple Hamiltonian just turns out to be v. And you can view this as, again, velocity or momentum. And the rate of change of velocity, which is acceleration, or if you multiply it with mass, then it becomes force. This Hamilton said that this should be equal to the negative of the partial derivative of the Hamiltonian with respect to x. And in this simple case, it turns out to be nothing but the negative gradient of the function at your current point. And this starts looking more and more like Newton's law in this Newton's law in this very simple case. That force is equal to the negative of the potential, and this is just a trivial equation. So what are the properties of this? So there are three interesting properties. One is time reversibility, which is generally satisfied by all classical mechanics. Second would be the preservation of the Hamiltonian itself on trajectories. And third will be something really interesting, which will be the preservation of volume. So I'm going to tell you about all these three things. All of them are relatively simple to prove, but I'll still go over slowly over them so that in case you have questions, please feel free to interrupt and ask. So time reversibility means the following. Suppose you start at a point x with the velocity v, and you move for some time t, and you reach some new point x prime v prime. So you reach at a point x prime and you note the velocity vector v prime. Now just reverse the velocity vector in the opposite direction and go back the same time. You're going to reach back at the point you started at with the negative of the velocity you started at. Okay, I'll let you absorb this for 10 seconds. It's saying something very simple, that there is this kind of symmetry with respect to time in these dynamics, that you can go from a point for some time, reach another point with some velocity, just reverse the velocity and go back the same time, or go forward the same time, and you reach the same point back with the velocity pointing in the opposite direction. The second property is what is called Hamiltonian conservation. And this is, okay, so I should also mention here that this Hamiltonian that I have defined here does not depend on time. In principle, you could consider Hamiltonians that depend on time, and they will not satisfy this property. Okay, so this condition holds only for Hamiltonians where there is no time component in them. There's no kind of friction, if you might want to imagine. So the preservation of Hamiltonian along the trajectory just says that the time derivative of this Hamiltonian is 0. And why is that true? So we can just use the chain rule and write down the Hamiltonian's derivative as summation over all its components of the rate of change of the ith position vector times the change of the Hamiltonian with respect to the ith position variable, plus the same thing for the velocity. And this is 0 because you can just plug in these equations there. So dv by dt is the negative of the Hamiltonian with respect to x, and dx by dt is the positive partial of h with respect to v. If I use these two sets of equations, which are really vector equations, and plug them here coordinate by coordinate, I get a term by term cancellation. For every term on this first summation, there is exactly one term with a negative sign in the second summation, and so you get a 0. So this is this is easy. What may not be so straightforward to see being easy using multivariate calculus is that the Hamiltonian also preserves volume in the phase space. So let me first explain what this means before I write down mathematically. So what this means is the following, that you have this 2D dimensional space, the phase space. You take a small volume element and now do the following. For every point in this set, you compute the trajectory and see where you end up after some time t. And you do this for every point. So this volume here will move in the phase space. This volume element here will move in the phase space. And this volume preservation property really says that the volume is invariant. So while it may happen that if you just look at the volume restricted to the position space or just look at the volume restricted to the velocity space, this can fluctuate wildly, but the volume in the phase space doesn't change. So to prove that, it's also really a couple of line calculation. So there are multiple ways to prove this. One is to just compute the push forward measure and look at the Jacobian, and you can see that the determinant of something is 1. Perhaps a more calculus way to see this is to now in the phase space RD cross RD at a point xv, you define this vector field, dx by dt and dv by dt, and you compute the divergence of this vector field. So divergence is this, this thing here. And again, you can check, you can just see from these equations that if I plug this stuff in, I get 0. And divergence is a mathematical quantity which measures whether there are sources or sinks in a vector field. And divergence being 0 everywhere is equivalent to saying that the volume under these, so the volume element as it moves in this vector field, according to this vector field, doesn't change. Any questions about these basic properties of Hamiltonian dynamics? Okay, so let's keep moving. This idea of volume preservation in the phase space actually is very, very general. It's all looks very specific in the setting of the Hamilton's equation, but there is this whole area of mathematics called symplectic geometry, whose goal is to generalize this property of Hamiltonian dynamics to more complicated objects, like manifolds, for instance. And so that once you have some function from that manifold, there is a more or less automatic way to define Hamiltonian vector fields or to understand how trajectories of particles in that phase space would move. So I'm not going to go so much into this, but for people who want to look it up, this is a very interesting branch of mathematics, which I'm sure will show up in this program as well. Okay, so let's go back to the idealized Hamiltonian Monte Carlo, and let's try to state what we are going to see in this lecture today. So everything here is the same as the slide that you saw before, except that I have just included one more notation here, which is this var phi sub t. And this is nothing but the Hamiltonian flow in the phase space. So this function just gives you the position and the velocity after time capital T once you start from this position and this velocity. I hope you can see my cursor as well. So,
Yes.
okay. So the first thing that we're going to prove is that this Hamiltonian Monte Carlo preserves the density function. And the second thing we're going to see is some convergence bounds. In particular, when the function is strongly convex and smooth, then essentially its condition number determines the convergence time in the Wasserstein-2 distance. Okay, this is a result that was, so what I'm going to show you is actually from an adaptation from the paper of Mangubi and Smith, where the dependence is condition number squared. But actually, I'm going to show you something, a simplification of this, where the dependence is really just the condition number, which was proved in full generality by Chen and Wempala in 2019. And theorem also tells you how long you can run this process for. And there is a reason. I mean, you'll see a very a reason why we cannot run it for very, very long. But I think the point to really note and drive home here is that there is no dimension dependence here whatsoever. Okay, so this is, I don't know of any other family of algorithms, maybe there are, but I don't know, where we have this kind of a property.
Can I ask a
Of course.
question?
Yes.
I'm curious why you're emphasizing the lack of dimension dependence here, because to me, it seems this is like a continuous time process. And if you look at the continuous time Langevin process, it should also converge with like continuous time that has no dimension dependence. Like, is it all the dimension dependence in sampling sort of inherent in the?
Yes, but continuous time, but the continuous time Langevin dynamics is actually choosing, I mean, it's adding noise at every iteration. I mean, like it's here, I think that maybe I should clarify this. I mean, what this really means is that so it also, I mean, so okay, so one difference between Langevin and Hamiltonian Monte Carlo is that the continuous time Langevin actually keeps choosing a different velocity at every time. Here we just choose the velocity at the beginning of each phase and then let it run. It's a completely deterministic process for a very long time. Well, by a very long time, I mean something like a constant, which is independent of the dimension. So maybe it is, I mean, so to me, it was surprising. Maybe it's not surprising to some people. So, but yeah, I think this is the lack of the dimension dependence here is what led people to think that perhaps we can derive dimension-free sampling algorithms from this. Of course, when we start discretizing, we will lose some of it, but in the end, I will say a few words about it. Okay, so let's look at the first property, that HMC preserves the target density. So what do we want to prove here? We want to prove the following. So suppose you were to sample. So we are in RD cross RD, so there's a base measure. And so, you know, the density is with respect to that base measure. So we sample this point X comma V from this density with respect to the base measure. And then we take one step of HMC. And by one step, again, I mean that in the first, you just throw away the velocity, sample a random velocity, and then that's step 1A, if you may. And then step 1B would be to now run Hamiltonian dynamics, which is a deterministic process for time capital T. So what I would like to prove here, and the proof will be fit in this slide, is that the point X tilde, V tilde that you end up at for any T will also have the same density. I mean, that's what it means for the density to be invariant. So then you may ask, why do we need to even resample? Why don't we just keep doing this? Any ideas why? I don't know if I'm allowed to ask questions to the audience, but maybe at least just to kind of slow it down a little bit. If something like this were true, if you would believe something like this, why do we have any need to keep refreshing the velocity?
Oh, because what you actually want is to sample from, you want to sample on X, right, at the end. So there's some issue where as you evolve, the distribution of X and V separately will change. That would be my guess.
No, you can just ignore V at the end. Because if it is indeed true that XV was X tilde V tilde is sampled from pi, remember that pi has this form, which is pi. I mean, for this particular Hamiltonian, the distribution is, you can just ignore V and you'll get the right marginal that you're looking for.
Well, here for you, the issue is, I guess, that the Hamiltonian is preserved. So if you don't update V, you're always sampling that energy surface, right?
Right. Yeah, I think ergodicity is the concern also, right? I mean that we will not be given a, I mean, so the whole premise is spurious here. We will not be given a sample from pi. We will have to somehow start from some arbitrary point and then slowly move towards this target density. I'm just pointing out these things to kind of illustrate the differences between HMC and some of the other standard MCMC algorithms. Yeah, so we need to kind of bypass the fact that actually the energy is preserved because and we should be able to kind of reach the target density no matter where we start from. But anyway, let's first look at this this property. So there are two steps. The first, the refreshing velocity step. Let's look at that first. This is the easier part. So we pick this xi independent of everything, independent of all the xi's we have picked in the past and independent of the current position. And because it has the same marginal, and I mean, in some sense, that is the reason why we are picking xi from the normal distribution. If, for instance, and let me make this remark here, if, for instance, you would have picked a different Hamiltonian where, for example, instead of half V square, you had some local norm and you were measuring the length of V with respect to that local norm, then you would have to pick from the corresponding marginal. So that adds this extra computational burden on you. Sampling from a Gaussian is very simple, but sampling from something which is distributed according to Riemannian metric might be harder. So there is a direct relation between this half V square and the covariance matrix in this. In fact, the covariance matrix here is just the Hessian of this quadratic form. So this is kind of by design. So that's the reason why, in fact, we are sampling to have this property that once we kind of replace it, and if for whatever reason you chose some different Hamiltonian, then we would have sampled xi from the corresponding normal distribution with an appropriate covariance matrix. Okay, so this part I think is should be easy to follow and doesn't really use any property of Hamiltonian dynamics so far. The second part is where we're going to use all the properties that we have talked about so far and one additional property. So when now we have this z, the random velocity that we just added, and now we simulated the Hamiltonian dynamics for time capital T, and we reach this point x tilde v tilde. Now, x tilde, v tilde is the deterministic function of these things. So first, let's observe that using the symmetry of h with respect to the velocity component, time reversibility of the Hamiltonian, and the Hamiltonian conservation, we get the sequence of equalities, which I'm going to explain. So the first equality is just saying that the Hamiltonian does not change whether we have, if we reverse the sign of the velocity. Our Hamiltonian is just half z squared, so it doesn't really change if I plug in z or minus z. So we do this first. Then we use the time reversibility to note that if I started from x tilde in the direction minus v tilde and ran for capital time t, I would reach x minus z. So this point here, x minus z, is the same as this thing inside. So this red thing here is a consequence, red equality here is a consequence of time reversibility. And then we have, because this is just, so now here you started at x tilde minus v tilde and ran Hamiltonian dynamics for time t. We know that Hamiltonian dynamics preserves the Hamiltonian. So we recover h of x tilde minus v tilde. And now we can again use the symmetry of the Hamiltonian to get x tilde v tilde. So we have used 2 out of the 3 properties of the Hamiltonian dynamics to argue that the Hamiltonian at your starting point is the same as the Hamiltonian at your ending point for all t.
Can I ask a question?
Yeah.
Why did you need to invoke the time reversibility here? It seems like it should just be Hamiltonian conservation.
I'm sorry?
Why did you need to invoke time reversibility here? Like, isn't this just a consequence of the Hamiltonian conservation?
I mean, I want to compare the Hamiltonian at this point to the Hamiltonian at this point. So I need some way to relate these things. And this is not a time, unless I'm missing something here. This is not a, yeah, so this, to do this, we need to go via this intermediate step.
I
I
think
think he's suggesting you start from the right and you just replace x tilde v tilde by phi t of x psi, and then you just remove the phi c, the phi t. And then you just have h of x psi, which is your left hand side.
Yeah, perhaps you could do that.
You still have to set x tilde v tilde somewhere, right? Like, you start from the right, go that way. You're still trying to map x tilde v tilde to some point. All you know is the forward mapping.
Yeah.
Yeah, so I start on the right and I just talk about the pre-image of the map.
Yeah, so I think time reversibility is, first of all, it's a trivial fact, it's not a very deep fact. And the pre-image, you do need some kind of inversion. I mean, there is not some crazy function. I think that's all you need here. Perhaps you will need something if you try to do that formally. I mean, there is another way to see why you need time reversibility, right? Which is probably more apparent in this this line that I'm going to say. And suppose now you partition the phase space into these infinitesimal cubes. Now I'm giving you a more graphic proof of this fact, right? So you partition this phase space into very small cubes, and they are so small that in each cube the value of the Hamiltonian is constant. Okay, and now let's say you move this cube in time. So the volume preservation thing tells us that the volume doesn't change. The Hamiltonian preservation tells us that the Hamiltonian doesn't change. So the density doesn't change as long as trajectories don't collide. So there has to be like a one-to-oneness in this. So if trajectories start colliding, then there is a problem here. So it's just it's some invertibility thing. That's all. It's not very deep. If I were to say which of the 3 conditions is most important here, I would say the volume one is the most important. And then the Hamiltonian one, and then the time reverse. But I mean, I think they are all necessary as far as I can tell. But I'll get back to if you send me an email, whoever asked this question, we can take it offline from there. Okay, so this is essentially, I mean, this is a sketch, but this is pretty precise. You can make it into a formal argument if you really are not convinced at this point that this is what is going on. And from here, you can also see that this argument will not apply in just the phase, in just the position space or just the velocity space, because the volume conservation is only in the phase space. You have to do this argument in the phase space. Okay, so let's get to the running time bounds. Whether how am I doing on time, just to get a sense of how quick or slow.
It's 4:14.
Okay, so 15 minutes or less.
Yes.
Okay. Okay, so what we're going to do is when we move towards convergence bounds, we're going to use the idea of coupling. So this is not new to people here, I presume. You have two Markov chains with the same transition kernel. We're going to construct a coupling, which is contractive. and the idea is, yeah, without any kind of further ado, the coupling that we are going to do is actually a very natural coupling once you start thinking of the process from a physics point of view. So there is, I mean, so there is one choice of randomness at this point, x1, which is what velocity to pick, and you have the same choice here at y1. X1 and y1 are two different positions. What we do is at every time step, we associate the same velocity, initial velocity. Of course, these velocities will change as the particle moves. The trajectories are different. So by the time it reaches x2 and y2, the velocity vectors will no longer be the same. Okay. So what shall we do? In the beginning, the velocities are the same. What we would like to understand is how long will these things keep moving so that there is some kind of a contraction between their positions. At some point, they will probably, so they will come, I mean, so this is something I'm going to show you first, and then give you kind of a proof of this. That for some initial time, they will come close to each other, these 2 points, given the fact that they have the same velocity. This has to do with the geometry of the space we are in. And we will get an estimate of that time. As long as we can prove that the particles are coming close, we will let them keep going. And once when we are not sure, we're going to stop both of them and pick a random velocity and give it the same velocity to both. So they'll come back even, they'll come closer even more, keep coming closer, closer, closer until they collide. And the key fact is that you can, for strongly convex and smooth potentials, you can prove a contraction which is independent of the dimension. I'm going to show essentially the essence of this proof via a harmonic oscillator. The proof almost immediately generalizes. Case. So let's So feedback from, so can you see this animation? Is it visible? No? Yes?
Yeah, it's not really moving. Oh, maybe it's because, yeah.
Or it's not moving? Okay.
So we see the bar now. Okay, yeah, that works.
So what is happening here is that there are these two pendulums, which ideal pendulums, which red and the blue one, which we start off with the same velocity at different positions, but with the same velocity. And you can, from your own intuition, even if you cannot see this, from your own intuition, you should be able to kind of guess that for a very short time, howsoever small it is, the two pendulums are going to get closer. And then they will diverge again. So what we really want is an estimate on what is this time where we can guarantee that these things come close. So let's look at the absolute vanilla case, which is the case of a spherical harmonic oscillator. And then we're going to go from the spherical to a general harmonic oscillator. So here, the function is just half of x transpose x, which is just half of norm x squared, and the gradient of this is just x. So we will generalize this in the next slide, the setting where there is even a diagonal matrix here, which is which assigns different weights to different coordinates. But let's just look at this simple case to get the intuition. And even if you understand this slide, I think that's already my job more than 80% done. And so let's give some, let's introduce some notation. So we have these two particles. One we are indexing with x and v, and the other one we are indexing with y and u. Both start off at different positions, capital X, capital Y, but with the same velocity, z. And this is where things are at after time t. So let's look at the second derivative of the difference in the position coordinates. Okay. So just by linearity, this is just the change of, the rate of change of the velocity of the first minus the change of velocity of the second. This is just the acceleration of the difference. Because you want to argue, when is the difference getting smaller? I mean, both particles, both pendulums seem to be moving away. So we can only argue that they're getting closer, which means the distance is getting small. So if you just plug in the formulas here, the Hamiltonian dynamics, we get that the rate of change of velocity is minus the negative, the gradient of the function. And the gradient in this case is just x. So the x is a vector here, but nevertheless, it's just x. So what we get is the second order ODE, that the second time derivative of some quantity is equal to the negative of the same quantity. This is exactly a harmonic oscillator or the spring that I'm sure we all studied in high school in a physics course. And we all know what happens here. It's the, since the particles were started at with the same momentum or velocity, we have one boundary condition, which is that the rate of change of the difference is 0. And so you can just solve it analytically. And you get that xt minus yt behaves like cosine of t times the initial difference. Now, this is not 0. But after time t, which is pi by 2, this will be 0. Cos pi by 2 is 0. I hope I got this right. And as a consequence, xt minus yt is 0. So this actually shows a single step contraction. In one step, you're going to hit this other thing. Of course, this is a very idealized situation, but at least you get some simple toy example where things are contracting. And this is something I believe doesn't require more than very basic math. Okay, let's do a slightly more tricky case, which is also not very far away from the general case of smooth and lock concave potentials. Any questions?
I have a question. So if I'm understanding correctly, does that mean you have to tune the time like appropriately?
Yes, absolutely. We are trying to get an estimate on time. And we will see already in the next example that this time will not be pi by 2. It will start depending upon the diagonal matrix that we're going to plug in here. Yeah, that's our goal, to get a bound on a time, the largest t that we can get where we have contraction. We know we have instantaneous contraction, that can be proved in a variety of ways because the space has kind of geometry where trajectories initially point towards each other, but we want to get kind of quantitative bounds. And that's what we're trying to get here. So now let's look at this more general harmonic oscillator where we have a diagonal matrix C where all CIs are positive. They are not the same, but they are upper bounded by capital M. So let's say all CIs are between small m and capital M, which is the case we are trying to mimic of if the function was strongly convex, then its Hessian at any point will be at least small m times identity and upper bounded by capital M time identity if it was capital M smooth. So we can do the same calculation. We will follow the same recipe, compute the second derivative of the difference in the position with respect to time. Now, instead of the identity here, we get this matrix C. There's a factor of 2 here because I dropped the half. You can ignore that. That's not going to make such a big difference. Now, because C is positive, this has a component in the direction of yt minus xt. This is important to note here. If C was not positive, these things may not converge. But because C is positive, there will be, so the time derivative squared of this quantity here will have some component in this direction, yt minus xt. So there is an attractive force. And as a consequence, I mean, very roughly, if two particles start with the same velocity, they will move towards each other at this rate. You don't have to understand how I came up with this, but it will not take you more than a minute to figure this out if you just sit down and do this for yourself. So there will be contraction. So that's, but however, there is a problem because we are not in the case where, in the identity case, essentially. So it's not like it's constant times identity. It could have potentially different numbers on the diagonal. It also has components which are not in the direction of xt minus yt, and that will tend to kind of pull these things away quickly. However, these ODEs are separable along the coordinate directions, and for every j, we can write down this evolution equation, second order equations, where now these are real numbers. Xtj and ytj, these are the jth coordinates of these vectors. So this case is very similar to the thing we just did before. Instead of cos t, you're going to get cos of square root 2 times cjt. So that's the solution to this. We know that Cj is bounded by capital M for all j, and so the contraction will happen till about this time now. So instead of pi by 2, we lose essentially inversely proportional to the square root of the bound we have on how large some C can be. And we also have a lower bound on these CJs. We know that each CJ is at least some small m. So we can also get basically this kind of a bound, that contraction. So for up till the time it contracts, the contraction can be bounded by something like this. And this is a number which is less than 1. You can use a very simple inequality involving cosine of a number s. And as a consequence, obtain a coordinate-wise contraction, which then gives you a vector-wise contraction of something like 1 over inverse of the condition number. And that's it. So we have a contraction which is like 1 minus m by m, or small m by capital M. And so we will converge in time roughly capital M by M, or the condition number of this potential. And this generalizes to the full case by essentially some simple comparison theorems that you will lose an additional factor of kappa in the analysis that I presented in the notes. But it's also not the tightest analysis. As I said, that you can actually get kappa as Chen and Wimpala did for the general case as well. Any questions?
Sorry, there's no T in this right-hand side anymore? You just upper bounded by a capital T?
No. So T is bounded by, so there is a T. Sorry, I think, so T is bounded by this quantity here. So this happens for T up till this capital T, which is pi by 2 by 1 over root 2m. So up till this time, you have contraction, and that contraction is this much.
I had a question also. Can you share the intuition for why initially trajectories point towards one another? In general, I guess.
Yeah, so these things are true very generally, actually, on even for very general Hamiltonians. So you have to do a curvature calculation for that, essentially. And the curvature turns out to have the right sign for positive geometries. I think these are called the Roch theorem or something like that in Riemannian geometry. So yeah, I can point to the precise place where you can find such theorems. But yeah, there is, yeah, I mean, I didn't want to make it very complicated mathematically, but yeah, there is already some reason to believe that there will be at least instantaneous contraction. But I mean, it is essentially as simple in local coordinates as this equation. If locally the equation of evolution looks like, the second derivative is minus d2x by dt, d2z by dt squared is minus 2z, then you know that contraction will happen. It's some constant.
So just one clarification. So the reason why, so it's just a matter of the proof technique here. So if you were in 1D, you would have a T at which they actually collide exactly, and you would probably think
that's correct. That's right.
And actually, you wouldn't do anything. You would just analyze it this way, but for your coupling. But here, like the two pendula in high dimensions are actually never touching each other. Is that what's happening?
They're not. That's right.
Like,
and in fact, that's a very good point. I should have mentioned that if your potential, if you were to sample from a Gaussian distribution using this method, you will do it in one step.
Okay.
Because that's what the harmonic oscillator corresponds to, the spherical harmonic. So this exactly corresponds to sampling from a Gaussian density. Because remember that our goal was to sample from e to the minus f of x. And this is already a hard case for many previous algorithms.
Okay, so I have a follow-up question. This is, I'm just thinking you're not going to go much. So this morning, Andreas mentioned the fact that you can use this coupling where you're just canceling out the noise for each of those parts. So here you're canceling out by taking the same velocity for in each of the realizations.
Yeah,
and
same thing.
Eventually you could actually try to have those velocities pointing towards each other, right? Like just drawing two correlated Gaussians that are pointing to each other and use the noise to actually get faster there. Is there anything to hope to gain, or there's actually really nothing to gain beyond what you already have by getting?
No, I think it's a good question, and this is still not a fully understood thing, I must say. So
if M is 0, for example, Is there that you could actually get there? Because you're not going to get contraction from your potential from the deterministic part, right? You need to actually, you should hope to get it from the stochastic part. So here you assume that your lowest eigenvalue is bounded away from 0, right?
That's right. It's a small m. Yeah. 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 I think that so that has to do with also the curvature of the the X space essentially. Yeah. Okay. Since I think I'm out of time, I'll just mention a few words about an integrator and then proceed to concluding the talk. So for those of you who probably I would say, okay, all this sounds great. I mean, how do we actually implement this? So even there are some very beautiful integrators, ways to discretize Hamiltonian dynamics, which is very unusual. I mean, the first thing that should come to somebody's mind is, why don't we just do Euler discretization, first order or second order Euler discretization? I just want to write these formulas in front of you without kind of trying to explain this to you, that there are these kind of discretizations or integrators, as they are called, where you don't lose all the good properties of the continuous dynamics. So in particular, there is something called the symplectic integrator, where even though the trajectories that it produces are not the trajectories of the Hamiltonian dynamics exactly, yet it conserves the volume, which turned out to be one of the key things in our analysis. And that ensures that the measure is being pushed forward in the phase space in the right manner. And it also approximately conserves the Hamiltonian. So I can't say much more than that. As you can see, these integrators require like really one gradient call. I mean, there are two gradients here, but one is from the previous iteration and one is the new iteration. The real question is, can we now give some kind of a bound on eta? And for this, I'm going to just mention one of my results. Perhaps that's the reason why I was asked to give this talk, that we can get d to the 1/4 gradient evaluations, which is beyond the root d bound with this Leapfrog integrator under certain regularity assumptions. And I'm thinking I'm going to skip the regularity assumptions and just mention that these regularity assumptions were inspired by certain Bayesian inference applications that appear in machine learning. Okay, so if you didn't follow any of this stuff, the take home is that discretizing Hamiltonian trajectories is an equally interesting topic in itself. Perhaps can be a talk in one of the workshops, or else, else during another time in the semester. And the punchline is, when we want to discretize continuous time trajectories, there is more you could possibly do than just doing Euler or Taylor series discretization. That's a take home for the general audience here. So to conclude, HMC is this sampling algorithm that really uses ideas from classical physics. In the ideal case, which I presented, there is no need for a metropolis step, giving it the promise to be fast and possibly have a small dimension independent running time. I talked about the second order, or at least I flashed to the second order discretization. There are also higher order discretizations by Yintat Lee and Santosh Vempala and others. You should look at which can get these bounds even better. From d to the 1/4, you can go down to d to the 1/2 times L, where L is essentially the bound on the Lth order derivatives of the potential function. There's lots of recent work on it. Riemannian manifolds, if you're interested in learning how to do HMC on Riemannian manifolds, while the Lee and Vempala paper does not really introduce a Riemannian HMC, it gives a non-asymptotic bound for in this setting. If you want to look at, so one of the issues which I flashed through was that once you start doing discretizations, you start getting running time bounds which depend 1 over epsilon as opposed to log 1 over epsilon, as in the continuous case. So for that, you'll have to metropolize the HMC again. You don't lose everything. You can still get pretty good algorithms. You can look at this paper by Yuan-Chi Chen and others from Berkeley who might be there. And Andreas Eberle and his co-authors have this very nice result, which shows coupling arguments which go beyond convexity. I guess I'll just conclude by saying that physics and physical systems have been and can be a great source and ideas for algorithms for optimization and sampling. And you will see more examples of this on Friday in the bootcamp. With this, I'll stop and take any questions. Thank you.
Any questions? Okay, you have one in the back.
Yeah, from the lecture in the morning, there were actually like 2 different techniques for analyzing sampling algorithm. And one of them was like using functional inequalities. And I was just wondering whether you can also like consider like a continuous version of like HMC by just considering like the noises like injected like continuously and somehow like analyze it using like functional inequality to achieve like
right. That becomes a Langevin dynamics actually. So if I make this time capital T to be close to 0, then it starts converging towards Langevin dynamics, and for which we do know how to do the kind of analysis that you're talking about.
Yes. Okay, thank you.
So my impression from speaking to practitioners, which I guess is sort of constant with your result, is that HMC is spectacular for sampling from a unimodal distribution. But if you want to sample from something that is multimodal, it's a disaster. So I guess I'm wondering, and maybe you've thought about this also, do you have any ideas for this sort of symplectic dynamics style sampling algorithm that would work for like not only non-convex but multimodal distribution sampling?
So actually, this paper of Bourabi, Eberle, and Zimmer does talk about multimodal distributions. So I'm not an expert in either practice or theory of these things. So I wouldn't comment on that, but I'll just point you to this paper, which is, I think, a very interesting paper, which talks about, which gives coupling bounds for multimodal distributions. And I think, but from what I understand is, and talking to some people who work in chemistry and use these methods in simulating molecular dynamics, I understand that the landscape there are very, very, non-convex, whatever that means. And they are somehow able to use HMC type methods to simulate, whatever they want it for. However, they do use dimensionality reduction methods in this. So in practice, I guess the situation is far more complex than anything that you have seen, at least in this talk. But thanks for that question. Yeah, I will certainly think more about it after your question.
Yeah, it's certainly. I just like the thing with, say, stochastic gradient descent or Langevin dynamics or something. So if you have a particle that's stuck in one mode and it needs to get to the other mode, every step you're injecting noise, right? Whereas with HMC, you have to wait and to capital T every time to have another chance of getting it to hop over to the other well, right? That's the sort of my understanding, heuristic understanding of what is the problem for HMC type of methods with this type of problem.
Yeah, and I should also mention that Andrei Ristevsky, who's I think visiting this semester, also has thought about this with, I think, Holden Lee and others on this multimodal thing. So he will also be a good person to talk to. I think he already has some results on this topic. But yeah, for multimodal sampling from multimodal densities.
Andrew, you need to post it on Discord because this is going to disappear with the talk.
All right, is there any more questions? All right, let's thank our speaker, Nisheeth.
Thank you.